Good evening everyone and welcome to another lecture of engineering mechanics. This is lecture number 9 and in this lecture we are going to start the concept of friction. So today we are going to learn about Coulomb's dry friction. Now what do we mean by Coulomb's dry friction? Let's understand that. But before we start with today's lecture, let's solve the assignment problem that I gave you in last class. A three-hinged arc is loaded as shown in figure. Which one or more of the following statements is or are correct? And this was an MSQ question, so there are multiple possible answers to this question. Horizontal reaction at A is W by 3, horizontal reaction at B is W by 3, vertical reaction at A is W by 4 and vertical reaction at B is 3W by 4. So you can see that we have an arc which is hinged at A, B and at the center. If I draw the free body diagram of this arc, how many unknowns do I get? Let's see. Let's say this is my arc. This is my arc. This is A and this is B. Let's consider this to be C, and between A and C there is another point which is D. Now there is a load W acting at D. Okay, I have isolated this this arc from the supports at A and B. At A and B you have hinge support, so you will get two reactions, one in X direction and one in Y direction, right? I don't know the direction of these reactions, whether it will be in plus X or minus X, plus Y or minus Y, so I will just assume some directions. Okay, so I will assume that the reaction at A in X direction is like this and in Y direction is like this, and I am naming it AX and AY. Similarly, here I will assume this direction BX and BY. Okay, so how many unknowns do you see in this free body diagram? You see 4 unknowns. You might be wondering why we are not considering the reaction at hinge C, because we have not isolated it from any other body, right? At C, was there any other body connected to this? No. This is an internal hinge. This is known as an internal hinge. It is internal to the body. So another body is not connected to this body using this hinge. So that is why we are not getting any reaction at point C right now. If you remove AC and BC, if you disconnect AC and BC, then you get reactions at C. But right now both are connected to each other, AC and BC. So equal and opposite forces are acting at C. So they are cancelled. Now we have 4 unknowns and we have only 3 equilibrium equations. So is it a statically indeterminate problem? No. Right now in this particular free body diagram, we have more unknowns and less equilibrium equation, but we can still solve this problem. Okay, first of all, whatever equations you have for this free body diagram, you apply those equations. So the first equation I have is summation of fx equal to 0, and from there I will get ax equal to bx. Now the second equilibrium equation I will apply is I will take moment at either A or B. Let's take moment at B. So if I take moment at B, the moment of reactions Bx and By will become 0 because both are acting at B. The moment of Ax will also be 0. Okay, because Ax is also passing through B. So I will get the moment of Ay and W. what will be the moment of AY? AY multiplied by this distance, and how much is it? L plus 2L, it is 4L, and this moment is clockwise, and the moment of this W will be anti-clockwise. How much will it be? W into 3L. So from here I will get the value of AY, which is 3Y by 3W by 4. I have got the value of AY, 3W by 4. So vertical reaction at A is 3W by 4, but here it is written W by 4. So this is wrong. Now I will calculate the vertical reaction at B using this summation of Fy equal to 0. So I will get AY plus BY equal to W. So what will be the value of BY? W minus AY means W by 4. So BY is W by 4, and here it is written that vertical reaction at B is 3W by 4. See, they have interchanged the answers. So these two statements are incorrect. Now we need to find out whether A and B are correct or not. Okay. So how to calculate the horizontal reaction at A and B? From this particular free body diagram, we can never find it out. So we need to draw another free body diagram. We will either draw the free body diagram of AC, or we will draw the free body diagram of BC. We don't need to draw the FBD of both. We just need the FBD of either AC or BC. Let's draw the FBD of BC. So if I draw the FBD of BC, this is B, this is C. At point B, we already have two reactions, BY, which is W by 4, and BX. Now at point C, we had a hinge joint, and now we have isolated BC from AC through this hinge joint. So I will get two reactions here. I am assuming their directions, CX and CY. Now I don't need to find CX and CY. If I want to, I can, but I don't need to. Now I need the value of BX. So what I will do is, I will take moment at point C. So if I take moment at point C, moment of CX and CY will become 0. Moment of BX will be anti-clockwise. It will be BX multiplied by this height. What is this height? It is mentioned 1.5L. And moment of BY will be, moment of BX is clockwise, moment of BY will be anti-clockwise, minus W by 4 into 2L. This is the center, na? 2L. So from here, I will get BX equal to W by 3. And if BX is W by 3, so will be AX. So both are W by 3 and W by 3. So A and B are the correct statements. You can solve this problem by drawing the FBD of AC also. Although I don't need to draw it, but I will still draw it so that you will understand. If you draw the FBD of AC, how is it going to look? So this will be the FBD of AC. This is A, this is C, somewhere here is D. W is acting at D. This is AX and AY, right? Now understand this. If you have drawn CX, CY at C like this, then it will be equal and opposite here. So CX is towards right here, so it will be towards left here. CY is downward here, so it will be upward here. Okay. So whatever directions of CX and CY you draw at AC, it should be equal and opposite at BC. So I will draw them in the same on the same page for better understanding. So this is Cx, this is Cy. So on the same page I have drawn the free body diagrams of AC and BC. Okay, so you can see at point C they are equal and opposite forces. If I draw both of them connected together, then these forces gets cancelled out and you get FBD like this. But if I separate them, then I get FBD like this. Now one more thing here I need to mention is I am getting all the answers positive because my directions, whatever directions I have assumed, they are all correct. If you assume Bx like this, you will get negative value of Bx. Okay. Now let's move on to today's lecture. So today we are starting a fresh new chapter called friction and its applications. And in that chapter, in this lecture, we are going to learn about the concept of friction, laws of dry friction, friction angle, angle of repose. Means we are going to study the basic concepts related to friction. Before we start solving numericals related to friction, we need to first understand the basic concepts. So let's talk about friction. We all experience friction in our day-to-day life, right? But what is exactly friction? Friction is a force of nature. Friction is a force which opposes the relative motion between two surfaces. Whenever two surfaces come in contact with each other and they try to move related to each other, there will be some type of opposition to this motion. There will be some force which will oppose this motion, and that concept is known as friction. Now friction can be between two dry surfaces or two wet surfaces. What do we mean by wet surfaces? If there is some lubricating fluid between two surfaces, then we will call it friction between wet surfaces, also known as wet friction. If there is no lubrication between two surfaces, it is known as dry friction. Now why I am telling you this is because the concepts of dry friction and wet friction are completely different. Why they are different? Because if there is a fluid between two surfaces, then we also need to apply the concept of fluid mechanics. In fluid mechanics, you will learn this concept of a fluid between two surfaces, moving between two surfaces. So when we consider wet friction, then we also need to apply the concept of fluid mechanics in that. We learn about wet friction in machine design. If you learn machine design, there you learn about bearings, and in bearings, when we lubricate the surfaces, then it becomes wet friction. But in engineering mechanics, we are going to study about only dry friction. So we are going to learn about the concepts of dry friction only. So dry friction occurs when unlubricated surfaces of two solids are in contact under a condition of sliding or a tendency to slide. Means it is not necessary that the surfaces are actually sliding past each other. Even if they are trying to slide, there will be friction. Now microscopically, how exactly this friction force is developed? Let's understand it using an example. Let's say that we have a white box which is fixed at the bottom. Let's assume it is fixed at the bottom, and on top of it there is a yellow color box. and now we are applying a force on this yellow box to move it towards right. Let's say that this force is very low. So right now it is not going to move. For example, if you have a heavy object near you right now, let's say a heavy bed or a heavy table or a heavy almirah or a heavy refrigerator, you try to push it using a very small force. Will it start to move? Will it start to move? No, it will not start to move. It means there is some force between these two surfaces which is opposing this force, right? If I apply a force on this yellow box and it is not starting to move, there must be some force between these two surfaces which is opposing this motion. There is a guy in the chat who is continuously spamming it. I would request either you stop or I will let you blocked, because this is a live class. Okay, whatever queries you have, I can answer that at the end of the class, but this is not the way to disturb the class. Okay. So if I apply a force on this box towards right and it is not moving towards right, it means there must be some force acting between these two surfaces. Now how that force is being developed, because I am not applying that force, right? So how that force is developed? In order to understand that, you need to get under the microscope. You need to watch the surfaces under the microscope. So let's watch these surfaces under a microscope. So if I look at these surfaces microscopically, what I see is, even if they look flat, they are not exactly flat. Right now you can see that the yellow surface is flat, the white surface is flat, but under the microscope you will see they are not exactly flat. They have these type of roughness on their surface. I am just drawing a very small portion, okay? So you can see that these surfaces have these type of irregularities. They are not exactly flat. So what happens is, when you apply a force like this, these surfaces, they get interlocked like this. There is one irregularity on top surface, there is one irregularity on bottom surface. They are locked. So you are applying a force, but they are not moving because these are locked. You can see here, at this point, at this point, at this point, at this point, they are locked, right? So at these points, you get forces like this, normal to the surface. These forces will be normal to the surface, okay? And right now I am drawing the force on the yellow box, okay? So at different points, you see we have these forces, right? Now, if you resolve these forces, you will see something like this on the yellow box. This is our yellow box, okay? I am applying a force like this. This force is P, okay? Now what is happening, understand? At these surfaces we have reaction forces like this. A lot of reaction forces, okay? So I am just, for example, I am just drawing 4 forces but there are infinite number of forces at every point. Okay, so if I resolve these forces, what I will get? I will get a normal force and a parallel force, a normal force and a parallel force, a normal force and a parallel force, a normal force and a parallel force. Let me call it N1, N2, N3, N4, and these parallel forces are F1, F2, F3, F4. So at every point you are getting two reactions. One is the normal reaction and other is the parallel reaction. Now this normal reaction we have seen in the previous chapter also, right? But there we were considering frictionless surfaces. Here we are getting these parallel reactions also, and these parallel reaction forces are known as friction forces. So now you understand how these friction forces are getting developed. Let me recap it for you. These surfaces are not exactly flat. They are irregular like this. At different points, you get reactions in different directions. And if you resolve these reactions, you get one normal force and one tangential or parallel force to the surface. And these tangential or parallel forces are known as friction forces. Now we are not going to consider the force at every point. What we are going to do is, we are going to take the resultant of all these forces. What we are going to do is, we are not going to take each and every point, right? We are not going to consider each and every point separately. So we will take the resultant of N1, N2, N3, N4, N5, N6 to infinity. We will consider only one single normal force, something like this. Let me call it N. Okay, and F1, F2, F3, F4, all these friction forces, we will consider one friction force, something like this, F. Okay, so this F is known as the friction force. So I hope now you understand the mechanism behind the friction force, how the friction force is getting developed. Now let's draw a graph between this force P and this F. I have not considered the weight of this body. Okay, let me draw the weight also. I have not considered the weight na. This is the weight W. Okay, so let's consider a graph between the force P and F. So let's say I am drawing P on horizontal axis and F on vertical axis. Okay, now let's say I start increasing this force P. What happens? Let's say we have a very heavy weight, okay, and we start applying force P and we start increasing this force P. Initially, as this body is very heavy, this body is not going to move because we are applying a very small force P. Okay, and as this body is not going to move, it will be in static equilibrium. So this F will be equal to P. Initially, when you are applying a very small force P, the body is not moving, so it is in static equilibrium. So F will be equal to P. So this graph will start from here. Now you keep on increasing the value of P. F will also increase. Let's say your P is 10 Newton, F will also be 10 Newton. Let's say your P is 50 Newton, F will also be 50 Newton. Let's say P is 100 Newton, F will also be 100 Newton. So you keep on increasing the value of P, F is also equally increasing. Why? Because the body is under static equilibrium. So summation of Fx must be 0. So P will be equal to F. But there will be a point when your friction force will reach its maximum value. This maximum value is known as limiting friction. This maximum value, F maximum, is known as limiting friction. What is it called? It is called limiting friction, and its value is given by F maximum equal to mu s into n. Now what is this mu s? This mu s is known as static coefficient of friction. What is mu s? It is known as static coefficient of friction. It's a constant value and its value depends on material. For different material, we have different values of mu s. Okay, depending upon their surface roughness, we have different values of mu s. Okay, why their value depends on material? Because different materials have different texture, right? For example, if you look at the metals, for example, if you look at the steel or if you look at aluminum, their surface is smooth, kind of smooth, not very smooth, but kind of smooth, right? So for them, the coefficient of friction will be a little less. But if you look at the surface of leather, it is rough. So for that, the coefficient of friction will be a little more. So depending upon different materials and their textures, there is different value of mu s. Okay. So this maximum friction force, also known as limiting friction, depends upon the value of this coefficient of friction mu s. Mu s multiplied by n. This is the maximum friction that can be developed between two surfaces, okay, during dry friction. So what happens if I increase my value of P further? Let's say I keep on increasing the value of P and I reach this point where it is, let's say, 1000 Newton. So this is the maximum value. Now friction force cannot be greater than this value, but your P can increase, na? So let's say I keep on increasing my P, 1100 Newton, 1200 Newton. So now what will happen? Until the value of F and P are equal, the body is not going to move. So till now, the body was not moving. Till now, the body was static, right? But at this point, my friction force is maximum. It has reached its limit. So if I increase my value of P even slightly, my F will become less than P So there will be a net force, right? Let's say P is 1100 Newton, F is 1000 Newton. So there is a net force of 100 Newton and that is going to move the body. So at this point, the body is on the verge of motion. On the verge of motion at this point. But after this point, what is going to happen? So after this point, your friction force suddenly drops and then it becomes constant and the body starts moving. Now, what is this constant friction force when the body is moving? This constant friction force when the body is moving is given by mu k into n. This is mu s into n and this is mu k into n. Now, what is mu k? So, mu k is known as kinetic coefficient of friction. What is kinetic coefficient of friction? See, for every material you have two coefficients of friction. One is static and one is kinetic. If the body is not moving, then the coefficient of friction is mu s, and if the body is moving, then the coefficient of friction is mu k, and this mu k is always less than mu s. So during the motion, the coefficient of friction gets reduced and its value is mu k. So for every material we have these two values, mu s, mu k. Mu k will be slightly less than mu s. For example, let's say mu s is 0.4, mu k is 0.3. Okay. So when the body starts moving, what happens is the friction force becomes constant. Now practically it does not happen. Practically this friction force, kinetic friction force, is not actually constant. Its value depends on velocity. Okay, its value depends on velocity. Practically, when the body is moving, then what will be the friction force? That depends upon the velocity of the body. But here we assume that for low velocities, the kinetic coefficient, the kinetic friction force is almost constant. So this is just an assumption, okay? Practically, this friction force will also vary with velocity. But for low velocities, we assume that kinetic friction force is constant and its value is mu k into n. Now, here in this chapter, we do not consider this part, kinetic part. Here in this chapter, we always assume that the body is static. We will consider only the questions where the body is static. When we will study about the kinetics of particles, kinetics of rigid bodies, there we will deal with problems related to this part. But here we will assume that we have only this part. Okay. In most of the problems, it will be mentioned that the body is just about to move, the motion is just about to start. It means we are here. Limiting friction. Okay, so what is limiting friction? It is the maximum possible value of friction force between two dry surfaces. Its value is given by mu s into n. If the force P is less than mu s into n, if P is less than mu s into n, body is static. And if P is greater than mu s into n, body is moving. Now what is P is equal to mu into N, mu s into N. So if P is equal to mu s into N, body is static, still static, and on the verge of motion. So even if P is equal to mu s into N, the body is still static. It is not actually moving, but it is on the verge of motion. Okay. So in this chapter, we will deal with problems where P will be either less than mu s into N or equal to mu s into N. But when we will study the kinetic part, then we will consider this part when P becomes greater than mu s into N. Okay. Now, this model of friction is not a proven law. This is just a theory which was proposed by Coulomb based on observation. So that is why it is known as Coulomb's dry friction. So what Coulomb did is he observed the cases, practical cases of friction. In laboratory, he performed some experiments. He observed how this friction force is actually behaving, and based on that he developed this theory so that we can solve the problems of static or kinetic friction using simple equations. Otherwise, if we get into the actual friction, then the problems will become very complicated. So whatever friction model we are using, whatever theory we are using, it is based on observations, based on practicals done by Coulomb, and based on that he developed this theory that okay, from here to here we can assume that friction force is equal to P. At this point we can assume that friction force becomes maximum. After this we can assume for low velocities that friction force is almost constant. Then for different materials he proposed that okay, this is the value of mu s, this is the value of mu k. So all this was done by him in laboratory based on certain experiments, based on observations. Okay, so this is the Coulomb's model of dry friction which we are using so that we can solve these problems simply. We can solve these problems using simple equations. Otherwise, practically the actual friction force will be slightly different than whatever we are applying here. Why? Understand this. Here we do not consider the area of contact. When I apply the friction force, I will assume that friction force is mu s into N or mu k into N. Here we are assuming that for material there is a constant value of mu s and mu k. But beta, for the same material, for different area of contact, there will be different friction, right? See, between my hands, if I put very less area of contact, there will be different friction, and if I increase my area of contact, there will be different friction, right? So based on area of contact, friction force is going to change. If less area is in contact and then the body is moving, there will be different friction force. If more area is in contact and then the body is moving, there will be different friction force. So friction force depends, actual friction force depends upon area of contact. But here in Coulomb's model of friction, we assume that the friction is independent of area of contact. Then in case of kinetics also, the actual friction force depends upon velocity, with what velocity the body is moving. For different velocities, the friction force will be different. But here we are assuming that it doesn't matter what is the velocity, the friction force is constant, mu k into N. And this is only possible for low velocities, okay? At high velocities, if you assume friction force to be mu k into N, you will get a very different answer. At low velocities also you will get different answer, but the error will be very less. But at high velocities, this error becomes greater. So Coulomb's dry friction model is not going to give us 100% accurate answer, but it will give us somewhat accurate answer so that we can proceed with our design. So that is why we are using this model, so that our equations can be easier. Now let's talk about friction angle, a very important concept related to friction. What do we mean by friction angle? In some problems, we will consider the normal force and friction force separately, but in some problems, we will take resultant of the normal and friction force. Okay. When we will take the resultant of normal and friction force, that depends upon the question, beta. Okay, it depends upon the question whether taking the separate forces will be easier or taking the resultant will be easier. But in some cases, we will see that instead of taking normal force and friction force separately, let's say this is the normal force, okay, and this is the friction force. Which friction force? Static friction force or kinetic friction force? Depends upon the question. Right now, let's assume static friction force, mu s into n. So in some cases, instead of taking these two forces separately, we'll consider their resultant. Let's say this is the resultant, R. Okay. The angle between this R and the normal force is known as friction angle. If it is a static friction force, this will be a static friction angle. If it is a kinetic friction force, it will be a kinetic friction angle. Okay, so it depends. Okay. So this phi is known as friction angle, which is the angle between the resultant and the normal force. If I calculate its value, it will be tan phi equal to this, means mu s into n, divided by this, means n, means mu s. So phi will be tan inverse of mu s, static friction angle. Kinetic friction angle will be tan inverse of mu k. Now what is the significance of this? Why we are studying about this friction angle? So it has different significance in different situations. Okay. For example, one significance, one use of this friction angle is, in some cases when you need to reduce number of forces, instead of considering n and mu n separately, you will replace them with their resultant. So where will this resultant act? It will act at an angle phi with normal force. Okay, normal force will be normal to the surface. So you know the direction of normal force. Take the resultant at an angle phi with normal force. Okay, so it can be used to replace n and mu n. Okay, so that is one use. And then there are other uses that you will see in future. Okay, even in different subjects you will be using this friction angle. Okay, for example, in machine design you will see the use of friction angle. Okay, so this is the very significant property, this is a very significant parameter known as friction angle, which is the angle between the normal force and the resultant of normal and friction force. Okay, let's move on to the next topic, which is angle of repose. Another very important topic, another very important concept. What is angle of repose? So angle of repose is what? Let's say that you have a body which is resting on an inclined surface. Okay, I am taking this body. Okay, this is a tube for my mouth ulcer and this is my notebook. Okay, so let's say I keep this tube on this so sorry, let's say I keep this tube on this surface. Okay, and I make it inclined. Now the angle of inclination is very less. So is this body moving? No, it is not moving. Now I keep on increasing this angle keep on increasing. There will be one point where it will drop. So at this particular angle, this tube is moving. See, but if it is less than this, the tube is not moving. If it is more, tube is moving. If it is less, tube is not moving. So you can say that at a particular angle, the tube starts moving. At a particular angle of inclination, this body starts moving. So that particular angle is known as angle of repose. So what is angle of repose? If a body is resting on an inclined surface, if a body is resting on an inclined surface, then the angle of repose is the angle of inclination at which the body starts to move, the body starts to slide. Let me call this angle theta. Okay. Now, how to find this theta? So let's assume that this body is just about to fall. Let's assume this body is just about to fall. That is angle of repose, na? The angle at which it is just about to move. It is just about to fall. Okay. Let's draw the free body diagram of this body, assuming it is just about to fall. Okay. Now here I will give you a very important tip. Whenever you are solving problems where the body is resting on inclined surface, always resolve your forces normal to the surface and parallel to the surface. Till now we were resolving the forces in horizontal and vertical direction, right? But whenever the body is resting on inclined surface, resolve the forces normal to the surface and parallel to the surface. Okay, not in x and y direction, this direction and this direction. Now the weight is acting vertically downward, na? So you will resolve the weight into two components. Now remember this, whenever you resolve the weight into two components, the component which is parallel to the surface will be the sine component. This will be W sine theta and this will be W cos theta. Okay, little bit of geometry you have to solve and you will understand how this is sine theta and that is cos theta. Okay, if you want me to explain, I will explain. Look at this. The weight is like this, na? The weight is like this. This is the horizontal component and this is the vertical component. Okay. Now look at this. This angle is theta. Okay, this angle is theta. And this angle is between the surface and horizontal. Now what is this? This is normal to the surface, right? Surface is making theta with horizontal, so normal to the surface will make theta with vertical. Normal to the surface will make theta with vertical. So this angle will be theta. So this becomes W cos theta and this becomes W sin theta. If you want another explanation, I can do this. If this is theta, this is 90 degree, then this will be 90 minus theta. Okay. So this will be 90 minus theta. So this is theta. Look at this triangle. This is theta. This is 90. So this is 90 minus theta. And if this is 90 minus theta, then this is theta. So this is cos component and this is sine component. Okay. So you remember this because you will have to do this quite a lot of times. So every time you can't find which one is the sine component, which one is the cos component. That is why I am asking you to just memorize this, that whenever you resolve the weight into two components, the weight component which is parallel to the surface will be sine component, normal to the surface cos component. Okay. Now there will be a normal reaction, normal to the surface. Let me call this normal reaction N. and we are assuming that this body is just about to fall down. So the friction force will be acting upward and it will be limiting friction because we are assuming it is just about to fall down, na? So it will be limiting friction. So its value will be mu s into n. Now, as this body is static, as this body is static, can I say that W cos theta is equal to n? Right? Can I say that W cos theta is equal to n and W sin theta equals to mu s into n? W sin theta is equal to mu s into n and W cos theta is equal to n, right? Because the body is static, so we can apply equilibrium equation. Net force must be 0. So n and W cos theta will be equal, W sin theta and mu s into n to n will be equal. Now if I take ratio of this, W and W will be cancelled. This will become tan theta, n and n will be cancelled. This will become mu s. Now what is mu s? Can I say mu s is tan phi? So theta will be equal to what? Theta will be equal to phi. So angle of repose is actually equal to friction angle. So beta, this is another use of friction angle. So friction angle is the angle of repose, means if a body is resting on an inclined surface, it will not fall down until the angle of inclination becomes greater than friction angle. The body will not fall down if you can say this, if theta is less than phi, body does not slide down. If theta is equal to phi, body is on the verge of sliding down, and if theta becomes greater than phi, then body slides down. So based on the value of phi, we can say whether a body on an inclined surface will fall down or not. If your angle of inclination is less than or equal to the friction angle, it will not fall down. But if the angle of inclination becomes greater than friction angle, then it will start falling down. So this is another very important and interesting significance of friction angle. Okay. So I hope that your basic concepts related to friction are cleared, because now we will have to solve problems related to friction. So we can divide the problems related to friction into two parts, two categories. Problems related to static friction and problems related to kinetic friction. As we are dealing with the statics part of engineering mechanics right now, we will only solve problems related to static friction in this chapter. Now when we will move on to the next part of engineering mechanics, that is kinetics, then we will be dealing with problems related to kinetic friction. Okay. Now I want you guys to solve this problem on your own. This is an assignment problem for you related to the concepts that we have just discussed. Okay. And we will be solving a lot more problems based on static friction in tomorrow's class. In tomorrow's class, I will deal with variety of problems based on static friction. Okay. So this is the assignment problem related to the problems we have discussed just now, the concepts we have discussed just now, and it is an MSQ question. So you have to check each and every statement. Okay. Now one of the student was asking what is the scope of aerospace astronomy, astrophysics, aerospace engineering. So I don't know about astrophysics, but I can say that aerospace engineering in some colleges it is good. So it depends. See, these type of branches is this type of branches, industrial engineering and operation research, energy science, ocean engineering. You can't say in general whether these branches are good or not, whether they have a good scope or not. Okay, these are known as interdisciplinary branches. Okay, because these branches deal with, these specializations deal with the knowledge of different domains. Okay, so these are interdisciplinary branches. So the scope of interdisciplinary branch depends upon the college. For example, at IIT Powai, IIT Mumbai, energy science and operation research, these two interdisciplinary branches, they have very huge scope. Very good companies come for placement there. But if you compare this energy science and operation research branch of other IITs and NITs, then there the placement is not that good. So you can't generalize that operation research is a very good branch. It depends upon which college you are talking about. Okay, chalo. So thank you so much for attending. I will see you tomorrow at the same time. Till then, bye bye, take care, good night.